First, let's do a little bit of practice with uh, traditional factoring. So notice that 4 and 10 are both composite numbers. So I need to try any of these cases. Just a reminder from previous units that if I have, for example, let's say 4x and x in here, I cannot put 10 or 2 in this spot because there's no greatest common factor in the original problem, and I can't invent a greatest common factor um, as things move along. So that's just something to keep in mind. If there was no GCF at the beginning, there's not going to be a GCF at the end. So I might be able to try 1 and 10 here, but that's not going to work. I might be able to try 5 and 2 here, and that does appear like it's going to work because 5 and 8 can end up making 3 if I make it a +8 and a -5. So if I distributed this back out, I would get 4x squared plus 3x minus 10. Then since I'm finding intercepts, I want to set the function equal to 0. So 4x minus 5 times x plus 2 equals 0, which means that my x-intercepts are at x equals 5/4 and x equals -2. Briefly, let's talk about what that means. That means that if I have f of 5/4, I know that that would equal 0. And if I have f of -2, that would equal 0. So essentially what's happening is if I substitute 5/4 into the equation, I'm going to end up with 0. That's something that's important to keep in mind as we move along also. So now let's try and factor this. The first thing I'm going to do is factor out a -1, just to make my factoring easier. 3 is prime, so 3x and x. And then 16 can be 16 times 1, 4 times 4, and 2 times 8. 2 and 8 are the most likely cases in this case because I needed to get to 2 in the middle. So if I need a -2 in the middle, I'll have 3x minus 8 and x plus 2. So if I set this equal to 0, I end up with x equals 8/3 and x equals -2 as my x-intercepts. So my x-intercepts would be at the point 8/3, 0, and -2, 0. And once again, just keep in mind that if I have f of 8/3, that would equal 0. And f of -2 would also equal 0. If I substituted these back into the original equation, I would end up getting 0. In this problem, there is a GCF. So I need to make sure that I see 2x as the GCF. I have x squared plus 4x plus 3. So I have 2x times x plus 3 times x plus 1, and I want to set that equal to 0. So my x-intercepts occur at x equals 0, x equals -3, and x equals -1. So my x-intercepts, if I were writing them as points, would be 0, 0, -3, 0, and -1, 0. And once again, a reminder that f of 0 equals 0, f of -3 equals 0, and f of -1 equals 0. Let's factor out a -1 to start. So x to the 4th minus 10x squared plus 9. This is something that we've talked about last unit on some worksheets when we have something with x to the 4th and x squared but no other terms. What we can do is we can treat this like it's a quadratic. So f of x equals negative x squared minus 9 times x squared minus 1. And then we can continue to factor this. So we have x minus 3, x plus 3, x minus 1, x plus 1. And so my x-intercepts in this problem would be at 3, 0, -3, 0, 1, 0, and -1, 0. We will quickly talk about the directions, since the directions said at the original start to find all x-intercepts. We're writing these as x-intercepts, which I neglected to do in the first problem. So 5, 4, 0, and negative 2, 0. But if the directions were slightly different, let's say the directions were, let's say the problems, instead of saying f of x equals, were 0 equals negative 3x squared plus 26x minus 16, for example. If that was the problem and it said solve for x, then what we would do is we would write our answer as x equals 8/3 and x equals negative 2. So it's important to understand what the directions are saying in the problem. Factoring the sum or difference of squares and cubes, a squared plus b squared has no real solutions. So there are no real solutions to these problems. There are no real x-intercepts, but we do remember that even though there are no real ones, we could factor this last chapter as a plus or minus bi, I'm sorry, a plus bi, a minus bi. Sorry, I was getting ahead of myself. A plus bi, a minus bi, and that would end up giving us the sum of two squares if I really wanted it that way. A squared minus b squared, that's a plus b, a minus b. That's something that I just have to memorize. I need to know how to factor that. So we'll get to a problem like that in problem 5. And then a cubed plus b cubed and a cubed minus b cubed, I'm going to have to memorize these. A plus b times a squared minus ab plus b squared. And then for a cubed minus b cubed, I get a minus b, a squared plus ab plus b squared. The acronym I like to use for this is SOAP. That stands for same, opposite, always positive. So notice that if the sign was originally positive, the first sign is the same, the second sign is opposite, and the third sign is always positive. If the sign was negative, the first sign was the same, second sign was opposite, third sign was always positive. SOAP, same, opposite, always positive. So that's important to keep in mind. 5, 6, 7, and 8. First thing, I'm going to set this equal to 0. There's a GCF here. I can factor this into x minus 5, x plus 5. So my intercepts are at 5, 0, negative 5, 0. And if the question was asking to solve for x and it was equal to 0 at the beginning, I would write 5 and negative 5 as my two answers. Number 6, here is our first example of a sum of two cubes. So notice that x cubed is really x cubed, and 8 is really 2 cubed. So my a in this case is x, and my b in this case is 2. So I have x plus 2 times x squared minus 2x plus 4. So notice I'm just taking a, substituting it in everywhere there's an a, and b, substituting it everywhere there is a b. And that's basically what happens in SOAP problems. You just have to memorize the stuff. Oh, I need to finish it. So if 0 equals this thing, the x-intercepts are at negative 2, and the answers to this, which are never real. These are never real. So they're always imaginary. And what I'm going to end up with when I do this, I'm only going to do it once. On 7 and 8, you're just going to have to trust me just for the interest of time. But x equals 2 plus or minus the square root of b squared minus 4ac all over 2 times a. So in this case, my other x-intercepts, which are imaginary, would be 2 plus or minus the square root of negative 12 over 2, which simplifies to 1 plus or minus I root 3. So those are my imaginary roots, comma 0, of course. Okay, in this one, I have the difference of two cubes. So f of x equals, um, first of all, I need to recognize what's being cubed. So 3x is being cubed, and 4 is being cubed. So my a is 3x and my b is 4. So I have 3x minus 4 because I have the same sign here. Then I have 9x squared because if I take 3x and I square it, I get 9x squared. Opposite sign, 3x times 4 is 12x, and then 4 squared is 16. So once again, this one's never going to be real. And then if I set 3x minus 4 equal to 0, I have an x-intercept at 4/3 0. The other two are non-real. Number 8, 0 equals, since I'm finding x-intercepts, I'm going to factor out a GCF. GCF is 4x, so I end up with x cubed plus 1. So 0 equals 4x times x plus 1 times x squared minus x plus 1, using same opposite always positive, because this is x being cubed and this is 1 being cubed. So I end up with x-intercepts at 0, -1, and then 2 imaginary answers. So my x-intercepts would be 0, 0, and -1, 0. Finally, factoring by grouping. If you have an even number of terms, you might be able to factor by grouping. It doesn't always work, but it's awesome if it does work. Step 1, group the terms into binomials or trinomials. So group them into groups of 2 or groups of 3. Step 2, factor out a GCF from each group. And then if the GCF that you factor out from each group ends up being leaving you with the same thing, then you can factor by grouping. So number 9, I'm going to group these into 2 groups of binomials. I'm going to factor out the GCF from each of these groups. So I have x squared times x minus 5. And then the GCF of the second group is 4. And when I factor out a minus 4, I'm left with x minus 5. Now, I can then factor out an x minus 5. So I have x minus 5 that I'm factoring out, and then what's left is x squared minus 4. This works out awesome because now I have x minus 5, x minus 2, x plus 2, and then I want to set this equal to 0 to find my x-intercepts. So x equals 5, 2, and -2. So my x-intercepts are at 5, 0, 2, 0, and -2, 0. I'll do another few examples. Let's group these two terms. So I'm going to set this equal to 0 since I'm finding x-intercepts. The GCF of the first 2 is 4x squared, and then I'm left with x plus 2. The GCF of the second pair is 9, and I'm left with x plus 2. It's very fortuitous for us that x plus 2 is left over in both terms. When that happens, that's awesome. I can factor out an x plus 2, and I'm left with 4x squared minus 9. Now, I'm just going to really briefly show you why this works. If I distribute this back out, I end up with 4x cubed minus 9x plus 8x squared minus 18. And if I rearranged these terms, I would end up with exactly what I started with. So after I pull out the 4x squared minus 9, the distributing does work back out. So I have x plus 2, and then 4x squared minus 9 is the difference of two perfect squares. So that's 2x minus 3, 2x plus 3. I end up with x equals -2, 3 halves, and -3 halves. So if I were asked for solving this equation, that would be what I get. But since I'm asked for x-intercepts, I'm going to write it as -2, 0, 3 halves, 0, and -3 halves, 0. I'm going to go a lot quicker through the last four, but I do want to give you as many examples as I can. So the greatest common factor of the first two terms is negative x squared, and I'm left with, let's see what I have, 2x minus 1. Then the greatest common factor of those terms is minus 3, and then I'm left with 2x minus 1. So I have 2x minus 1, and then I can have negative x squared minus 3. I can pull out a negative 1 from this, so I have negative times 2x minus 1, negative 1 times 2x minus 1, times x squared plus 3. So if I look at this, I get x equals 1/2, and x equals plus or minus the square root of 3i if I solve this one, but those aren't real x-intercepts, so I don't really have to write them as x-intercepts. So 1/2 comma 0 would be my answer. Number 4, I will group these. Oh, there's a GCF. We need to be careful. So f of x equals x times 6x to the third plus 18x squared plus 5x plus 15. Now I will group these two binomials. F of x equals x times, the greatest common factor of this is 6x squared, and I'm left with x plus 3. And then the greatest common factor of this is 5. I'm left with x plus 3. So I have 0 equals x times 6x squared plus 5 times x plus 3. And then I get x-intercepts at 0, negative 3, and then plus or minus the square root of, that was a weird way of writing that, plus or minus the square root of negative 5/6, which is I times the square root of 30 over 6. I'm not going to write that as a real x-intercept because it's not. So I end up with those. The last two problems require you to do a little bit different stuff. So in number 13, I'm going to group these into 3 binomials instead of 2 binomials. So notice that the greatest common factor of the first group is x to the fourth. The greatest common factor of the second group is negative 5x squared. And the greatest common factor of the third group is 4. We are very fortunate, as we have been in all of these problems on the back, where the numbers that end up being factored out leave us with x plus 1 every time. It's been leaving us with the same thing every time. And I'm sure once we start getting problems that don't leave us with the same thing every time, we're going to have to learn a new method. But as of right now, we're doing okay. So we have x plus 1 times x to the fourth minus 5x squared plus 4. And then I can factor this further into x squared minus 1 times x squared minus 4. So I can continue to factor this further. X squared minus 1 goes into x squared plus 1, or I'm sorry, x plus 1, x minus 1. So I can write x plus 1 squared because I have the original x plus 1 I had, and then I'm going to have a different one from the x squared minus 1. And then I have x plus 2, x minus 2. So my x-intercepts are at negative 1. It's a double root. 2, negative 2, and positive 1. I know I didn't write those in any particular order. So negative 1, 0, 1, 0, 2, 0, and negative 2, 0 are my x-intercepts. And again, this one would be a double root. Okay, number 14. On this problem, first thing I have to realize is that I have a greatest common factor. So I pull out the x, and I get x to the fifth minus 6x to the fourth plus 8x cubed minus 2x squared plus 12x minus 16. In this problem, if I tried to do it the same way that I did it in the last problem, if I factor out an x to the fourth, I'm left with x minus 6. Don't write this down. It's not going to work. If I'm factoring out the greatest common factor of this, I have 2x squared, and then I'm left with 4x squared minus 1. Notice that these aren't the same, so I don't even need to continue trying this. It's not going to work. So that is not going to be a way that I can factor this one by grouping. However, I can factor this one by grouping if I recognize that if I take these two trinomials and factor out the greatest common factor of the trinomial, I take the x cubed out, and I'm left with x squared minus 6x plus 8. And then I factor out a negative 2 from the back half, and then I'm left with x squared minus 6x plus 8. I can have x times x cubed minus 2 times x squared minus 6x plus 8. So the x is a factor. X squared minus 6x plus 8, I'm going to write that as x minus 4 times x minus 2. And then this x cubed minus 2, if I really wanted to, I could factor that into an irrational thing. I'm not going to keep it this way. I'll leave it in red real quick. But I could write that as x minus the cube root of 2 times x squared plus cube root of 2x, and then plus the cube root of 4. But I'm not expecting you to know how to do that with the radicals yet. So I just wanted to expose you to it. You could probably leave that as x cubed minus 2, and we'd be fine right now. So x equals 0, 4, 2, and then there are some answers that would be there. There's one real answer at the cube root of 2, and then there are two other imaginary answers. So I have 0, 0, 4, 0, 2, 0, and the cubed root of 2, 0 are my four real answers.